And now a variation on our Venturi tube problem. Let's take that same tube and empty it of water and turn it upside down like so. So we've got, like, say, a basin of water down here in blue, and then our tube is now filled with air in yellow at a pressure of 1 atmosphere. The open ends of the tube are dipped into the water down here, and we imagine that the tube is open on the left and on the right, so that eventually gas will be flowing through the tube from left to right. But at the moment, our state is hydrostatic equilibrium, so there's no flow anywhere. We've just got our tube dipped into this pool of water down here, and 1 atmosphere gas both inside and outside the tube. So if we want the pressure at points 1 and 2, then that's just atmospheric pressure, 1 atmosphere. And let's predict now what's going to happen if we start pumping gas through the tube from left to right. So we start to get a flow of gas in here that is separated from the surrounding air. So if gas starts flowing through here, we know based on the Bernoulli effect that here at 1, where the tube is wide, we will have a slow-moving, high-pressure gas, and then we'll have an acceleration zone here where the diameter changes, and then here at point 2 in the narrow diameter section, we will have low-pressure, high-speed gas. Point there being that if once we have flow from left to right, the pressure here at 1 should increase and the pressure here at 2 should decrease. And if the pressure at 1 increases, that means the gas here at this location is going to press down harder on the water below it. So we expect that this column of water inside the vertical part of the tube, that column of water will be pushed down once flow starts going through our pipe. Likewise, over here at point 2 or below point 2, if the pressure here at point 2 drops, then that should allow the water in this column here to rise up higher. So we're expecting these two columns to change in height once we start pumping gas through the tube. And our situation should then look like this. So now we've left hydrostatic equilibrium and we are in steady state flow, where we have a flow of gas Q coming in from the left, which will of course match the flow of gas Q going out at the right. I'm showing 3 streamlines here of flowing gas this time. And now here I've changed the color of the gas a little bit. In yellow is still the 1 atmospheric pressure surrounding gas in the room. And this more greenish color here is a slightly higher pressure gas coming at a slow speed through the wide section of pipe. And then this pale grayish blue over here is now the slightly lower pressure, fast moving gas moving through the narrow section of pipe. And we see how the high pressure gas here has pushed the water down out of that column, and the lower pressure here has allowed the water to rise up through that column. Our goal is going to be to compute the pressures down at A and B at the tops of these 2 different water columns. We want to find the pressures there, and then we want to find the speed of the gas here at point 1 and the speed of the gas there at point 2 as it passes through gates 1 and 2. Okay. Let's first make an approximation that since the density of gas is very low compared to the density of liquid, about 1 kilogram per cubic meter, then the difference in pressure as we go lower in our gas column here will be negligibly small. So the pressure here at point 1 should be about equal to the pressure here at point A at the gas-water interface, since the weight of this column of gas here is negligibly small. So pressure at 1 should match the pressure at A, and the pressure here at 2 should match the pressure at B, again, since the weight of that column of gas is negligibly small. But we do expect the pressure at 1 to be higher than the pressure at 2 based on the Bernoulli effect once we have flow, horizontal flow. Even though they're at the same horizontal height, they're different pressures once there's flow. However, in the vertical direction, our hydrostatic condition still holds. We can compare the pressures at two different vertical positions based on the difference in their vertical heights, D for that depth or vertical height there. So where should we compare the pressure at point A to? Let's pick this location right here. At the gas-water interface, some location there. We can compare that to A because there's no flow of fluid over in this part of the water, no vertical flow anyway, so our hydrostatic equation should apply comparing those two locations. So the pressure here at A should be equal to the atmospheric pressure, 1 atmosphere here at the gas-water interface, plus rho times g times the difference in height between those two locations. There's a 1 meter depth, and this would be the density of our liquid. Noting that the difference in pressure between these two locations is due to the weight of the water between those two locations. This column of water right here with a 1 meter depth to it. Okay, so that'll give us an estimate based on the density of water and little g, 9.8 or roughly about 10 newtons per kilogram, and this 1 meter difference in vertical height between those two locations. So that's 10 to the fourth newtons per square meter, or 10 to the fourth pascals, which is about 0.1 atmospheres, since 1 atmosphere is 10 to the fifth pascals. So 0.1 atmospheres plus 1, so 1.1 atmospheres would be the pressure here at A, a little bit higher than atmospheric pressure, pushing the water down out of that pipe. Over at B, we can also compare the pressure here at B to this point over here. There's a vertical difference of 2 meters between those 2 points, and the difference in pressure between those 2 points will be given by the weight of this column of water, this 2 meter tall column of water between those 2 points. So we'll say the pressure at B will be equal to the atmospheric pressure at this location here, at that gas-water interface, 1 atm right there, plus the density of water, of the liquid, times the depth, 2 meters between those two locations. So putting those values in, careful, we gotta be careful here about which is the higher pressure. Here, we're expecting that this is the higher pressure than at B. Since the gas pressure dropped here, water rose in this column due to the air pressure here being lower than the outside pressure. So the pressure at B is actually lower than the pressure out here at this point. That's why the water has risen in this column. So I've got to fix my sign right here in the equation. The pressure at B is lower than atmospheric pressure. So to find the pressure at B, we're going to take the atmospheric pressure and subtract this rho gh, or the rho g depth term. So 1 atmosphere minus density of water times g times that 2 meter column there. So we get this is about 0.2 atmospheres here. So 1 minus 0.2, 0.8 atmospheres. Lower pressure at B than at 1, and lower pressure at B than here, and higher pressure at A than here. So those are our two different pressures at A and B. Knowing that, we can now determine the speeds of the gas at gates 1 and 2 using the continuity equation and the Bernoulli equation. Continuity says that the flow rate at 1 equals the flow rate at Q. So the liters per second or gallons per minute or cubic meters per second. The A times V at gate 1 equals A times V at gate 2. We'll need to know what the cross-sectional areas at 1 and 2 are like. So suppose that the cross-sectional area at 1 is twice the cross-sectional area at 2. So if the area has gone down by a factor of 2, the speed will have to have gone up by a factor of 2, so those flow rates match. So our fluid will be going twice as fast at B as at A. And then let's apply the Bernoulli equation to this streamline in the gas. This streamline here at point 1 and at point 2. So the pressure plus the kinetic energy density at point 1 and the gravitational potential energy density at point 1 equals the sum of those same three terms at point 2. But note here that this row, that's the density of the fluid on the streamline. So that row is the density of the gas, not the density of water. Our gas density is about 1,000th of the density of water. So this 1 kilogram per cubic meter, that should be the density used in Bernoulli equation comparing points 1 and 2. That'll be these densities here and here. So comparing those two terms, they are at the same height. Z1 and Z2 are the same. So we can subtract those two terms, they'll cancel out. And let's start rearranging this to try and solve for the speed at gate 1. So we'll get the difference in pressures on one side and the difference in kinetic energy densities here. Then we'll replace speed 2 with double speed 1. Speed 2 gets squared, so that V2 squared becomes 4V1 squared. Factor out the 1/2 row. 4V1 squared minus V1 squared is 3V1 squared. Gets us here, and finish rearranging to get V1 by itself. Multiply both sides by 2/3, divide by row, square root to get us here. Then we know the pressures at 1 and 2, the high pressure at 1 in the wide section, the low pressure at 2 in the narrow section. That's a 0.3 atmosphere difference. 0.3 atmospheres is going to be about 0.3 atmospheres is 0.3 times 10 to the 5th pascals. 0.3 times 10 to the 5th pascals, since 10 to the 5th pascals in 1 atmosphere. And so we finished that calculation using the density of the gas here, not the density of water, but the density of gas, 1, not 1,000, to find the speed of that gas, that high speed right there at 0.1. And with that, going back to our continuity equation, if we know the speed at 1, then we know the speed at 2 is double that based on continuity. So we now have the speed of the gas at 0.2 as well. All right, and for a little visual comparison here, suppose here are our 3 Bernoulli terms at point 1. Could you fill in this bar graph at point 2? Noting how much kinetic energy we've gained and how much the pressure has changed. Yeah, you go ahead and do that. Pause the video a moment, use what you've learned, color in this bar graph at point 2. You got it? We know that since our speed doubled at point 2 and kinetic energy, the speed gets squared, then our kinetic energy went up by a factor of 4. So our kinetic energy density should be 4 times what it was at point 1. Our gravitational potential energy density has not changed since we're at the same vertical height. So those 3 units of kinetic energy density that we gained must have come from 3 units of pressure that we lost. So this red here is the 11 units of pressure at point 1, the high pressure point, and then these are the 8 units of pressure at point 2, the low pressure point, according to our Bernoulli effect here.